Let's go ahead and take our calculators out. And I'm going to have you put the following function into your calculator. Into y1, I want you to put the following function, square root of x minus 2 divided by x minus 4. I want you to set your minimum value to 0, your maximum value, I'd like you to set that to 7, your minimum y value, I want you to set to 0, and your maximum y value, I want you to set that to, let's say, 1. So those are the ones that I want you to put in. Let's see here.
Can I take this?
Yes. And it would show over that, wouldn't it? Minimize. Now I have to fight with my program to figure out how to clear it. Alright. So, y equals, and then square root x minus 2, close parenthesis, divided by parenthesis x minus 4, close parenthesis. Window key, x minimum 0, x maximum 7, y minimum is 0, y maximum is 1. Hit graph, and you get the following curve. Did everyone get that? Okay. Now, there's something that's not happening, that the calculator, Kate, is not showing you, okay? The calculator is showing you the curve for the most part, but notice that, go to the main window again and do this. Go to variables, y1, and let's calculate y1 of 4. Let's calculate y1 of 4. What do you get when you do y1 of 4?
Divided by 0.
What did what?
Oh, okay. Wait, bars, y bars, function, y1.
Yep, function y1, parentheses 4, close parentheses. And you should get this error here, divide by 0. Now, why is that happening?
It's 4, 0. Or no.
Go back to the original function.
Oh, because x is 4.
When x is 4, what particularly happens? You get 0 in the denominator, and that causes what? An undefined value. However, notice the graph here gives absolutely no indication whatsoever of that happening, right? Now that is a weakness in your TI 83 or 84. That's a weakness. The calculator doesn't show you that what happens, Kate, at 4 is you actually have what's called a hole. You have a hole at 4. So what I'm going to do real quick is I'm going to show you what the curve looks like with the hole in place. So I'm going to graph that same function on the axis. There we go. All right. So here we go. This is the curve right here. And what we actually have here is a hole at that point. Okay? Now, what I've got here is this vertical line right here represents the left-hand side of 4, and this vertical bar here represents the right-hand side of 4. And what happens is, in the limit, as I approach, I get closer and closer and closer. Look what's happening to this ordered pair here. It gets closer and closer and closer to that hole, to that limit point. Okay? Does that make sense? And as I move this right here, it gets closer and closer and closer and closer on the right-hand side to that hole, to that limit point. So we have a situation here, Seth. The situation is this. Even though that's an open hole, which means what? We can't plug 4 into the function. It does seem to be approaching something, doesn't it? It does seem to be approaching something. And that something is 1/4, 1/4. And now we're going to use our calculators to see that very fact. So here's what I want you to do.
Wait, how can you tell it was 1/4? I thought it was 4.
Well, the reason why it's 1/4, I'll go back to the graph real quick. What is x approaching, Sydney? If you said x is approaching 4, you're absolutely correct. But it's about what the function is approaching, the y values. What are the y values approaching? They're approaching 1/4. Look at the graph right here. What is the ordered pair at the open hole here? It's 4, 0.25, which is 1/4. So in other words, as x, let me zip this back. What is x at right here? X is at what? 2, right? Now what's happening? It's approaching 4 from the left. What's happening to the y value? It slides down the curve until it gets closer and closer to 0.25. That's what's happening. So now what I want you to do is to take your calculator, and I want you to go to something called table set. Table set is right here. It's above the window key. So you go second table set. And what I want you to do, Kate, is I want you to start your table at the number 3. And down here, this is called the table increment. And what I want you to do is I want you to go 0.1 increments, like that. So the first table starts at the number 3, and you're going to go in increments of 0.1. So it'll go 3, 3.1, 3.2, 3.3, 3.4, 3.5, on and on and on. So it's going to get closer to 4. So right above the graph key here, Joshua, is the word table. So you go second table. I want everyone to do that. And all of your calculators should be showing you this right here. Okay? So now what you do, Seth, is you scroll down. What is the x value getting closer to? 4. 3.9, and look at what happens at 3.9. We have 0.25158. Now, the moment I go to 4, it says error, because Doris, you can't divide by 0. But now I go on the other side of 4 at 4.1, and look what I have, 0.24846. So even the calculator is showing me, Abby, that it's approaching 0.25 as x gets closer and closer to 4. Does that make sense to you? All right, let's go back to table set real quick. Let's start at 3.9, and this time I want the increment to be 0.01. I want the increment to be 0.01. So we're going to start at 3.9, and the increment's going to be 0.01. Now I go back to table, so here's 3.9, and that means that I'm zooming in even closer now. 3.96, 3.97, 3.98. Look what happens when I'm at 3.99. It's 0.25016. The moment I hit 4, there's my error again, right? But I go on the other side of 4, and I get 0.24984. So what I'm trying to do, am I convincing you that as x gets closer to 4, the y values get closer and closer to 1/4? Okay? That's what I'm trying to convince you of. Okay? All right? Now, here's what we're going to do. We're going to take that same function. So I've got f of x equals the square root of x minus 2 over x minus 4. And what I'm going to do is I'm going to evaluate the function right at 4. And you're probably going to say, well, why on earth would you want to do that, Mr. Partridge? You already know that it's indeterminate. That's true, but I want to show you, Alexandra, what kind of an indeterminate it is. So what I do is I plug in 4, and I get the square root of 4 minus 2 over 4 minus 4. Well, I already know the square root of 4. It's 2, right? So 2 minus 2 over 4 minus 4, and that gives me something called 0 over 0. This is undefined. but it's a special kind of undefined. This kind of undefined is called indeterminate. Indeterminate. And whenever you get this, Kate, an indeterminate, that's usually, not always, that's usually a hint, Katie, that you're approaching something, but you can't plug the number actually in to the function. Okay? Does that make sense? You're usually approaching something. You may not be. You may be blowing up to infinity, but you may be approaching something. So you need to know what kind of indeterminate this is. This is a special undefined value called an indeterminate. Okay? All right. So let's talk about limits. Let's go back to the definition. The definition says, let's read it together from the book. If f of x becomes what? Arbitrarily, which means randomly close to a unique number, L, as x approaches c from either side, the limit of f of x as x approaches c is L. This is written as the following. The limit as x approaches c of f of x equals L. So this is the way that we usually do this. We draw some kind of general curve right here, and this is the point C on the x-axis. And we've got some kind of function curve. I'll put an open hole here, like so. Okay? And this is the function f of x. Now, what I'm going to do is I'm going to approach C from the left. And I need to show you what that looks like. It's written like this, Doris. The limit as x approaches C with a negative sign in the superscript position. That negative only means one thing. It doesn't mean C is negative. It simply means I'm approaching C from the left. That's all it means. Does that make sense? So I'm approaching C from this direction, right here. So what I'm doing is, if this is a point, the point is going in this direction, the ordered pair. So as x travels towards C, f of x is getting closer and closer to the open hole. Okay? All right, so what I do now, Seth, is I want to approach from the right. I need to say f of x here. Now I need to say the limit as x approaches C from the right. Well, you're smart. What would I put here? Positive. And all that means, it doesn't mean that the value of C is positive. It just means I'm approaching from the right of f of x. He's giving more of a watered-down version of the limit, is what he's doing. It's not necessarily wrong. What he's doing, Seth, is he's saving the definition of the limit more for calculus. But the problem is, you really can't do that because a limit by its very nature is two-directional. You have to approach from both directions. Okay? So what we're doing is, we're going to call this ordered pair right here. This open hole is at the ordered pair C, comma L. So what is the limit as x goes to C from the left of the function? Well, what are the y values approaching? They're approaching capital L. And as I approach C from the right, what are the y values approaching? Again, well, the same capital L, right? Do you see that visually? Okay? So what we say here, and this is really the important factor, if these two things are the same, if the left-hand approach is the same as the right-hand approach, then the limit exists. Then the limit exists, and I can finally say the limit as x approaches C of f of x is equal to L. You see, say that again?
Would they not be the same?
Oh, I'm going to show you a case where they're not the same. I am going to show you one.
So, when you just say like the whole thing, if when
Yep.
C approaches
As x approaches C from the left, if the function approaches L, the function approaches L, okay? What is that, Abby? That's a y value, okay? And as x approaches c from the right, if the function approaches L, in other words, if they approach the same thing, then we can say the limit exists, and the limit of the function is the value of L. Notice down here, Joshua, there's no plus or minus. Why? Because it's two-directional. It's both left and right. And that's what you wouldn't get in this lesson. You'd get the impression that a limit can just be approached from either way. That's not true, Kate. The limit has to be approached from both directions to exist. Okay? All right, so Sydney asked a good question. She said, okay, when wouldn't it exist? Well, let me give you a case of that. Here's f of x is equal to, here's a piecewise function, x plus 3, as long as x is greater than or equal to 1, and it's equal to negative x when x is less than 1. So this is a piecewise function. So what I do now is I graph the piecewise function. Here's my y-axis, here's my x-axis. I'll put the function in blue. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, what is f of 1? F of 1 is what? Well, you have to go over here. Which of these conditions allows x to be the value 1? It's the top one, right? So I put 1 in here, Seth. 1 plus 3 is 4. So I know that this is at 1 comma 4. And what's going to happen is it's going to go off in this direction, like this. If I plug in 2 and 3 and 4, I'll just get the same line right here. Now, what happens when I plug in f of 0? Which condition here allows for x to be 0? This one right here, so it goes in this direction. However, this line does let me get close to 1. I just can't equal 1, right? So I could plug in 0.99, right? Is 0.99 less than 1? Okay. So I could put in, I went the wrong direction with this. I apologize for that. I don't know why I did that. There we go. It's negative x. It goes this way.
Sad. My paper looks so neat.
Well, for x less than 1. So, come on. Come on, Partridge, do this. Here we go. Woo! Man. There
Are
we
you
go.
kidding me?
Nope. I'm sorry, Abby. I'm ruining your eraser. I know.
I don't even have a razor.
Never do it in pen. All right, but
I do my notes.
just a second. If I put f of negative 1, negative 1 goes in here, right? So it's negative negative 1, which gives you positive 1. So that's why it goes like this. Okay? Negative 1, positive 1. Okay. However, I can get close to 1, right? I could plug in, say, f of 0.99, right? Is 0.99 less than 1? So if I plug in 0.99, what does it become? Negative 0.99. So what's happening here, Sydney, is I have an open hole here at x equals 1, y equals negative 1, because this lets me get real close to 1, and the y value gets real close to negative 1, but it's not defined at that point. So I have an open hole. This is not a good time to get a call. Go away. Okay. All right, now, what happens if I take the limit as x approaches 1 from the left of the function? So what you need to do, Seth, is you just need to follow the curve. Here's an ordered pair. I'm going in this direction. I'm approaching 1 from the left. So what are the y values doing as I travel this curve? I'm going towards what y value here? Negative 1. So that means that the limit as x goes to 1 from the left of the function is negative 1 from the picture. Does that make sense? Kind of. All right, let's follow this now from the right. Choose an ordered pair here, Seth. I'm going to travel this direction from the right on the x-axis. What's the ordered pair going to do? It's going to go down, right? Now, what's it getting closer to as x approaches 1 down here? The y value is getting closer to what? 4. So the limit as x goes to 1 from the right of the function is equal to the number 4. So here's a case, Sydney, where the left and the right-hand limits do not agree, which means the limit itself does not exist. The limit itself does not exist.
So we have to take like piecewise functions and graph.
Yep.
Because that's what I don't think I can do. I get the other part.
Then we're gonna need to practice on our
Well,
piecewise
I can do it, but
functions.
it's confusing.
Well, we're just gonna have to work at it and hopefully make it as unconfusing as we can. I'll give you another one. Here's f of x is equal to, let's go ahead and say x squared for x greater than 0 and x plus 1 for x less than 0. All right, let's graph that. One, two, three, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, now let's go ahead and graph this out. I need to put a greater than or equal to here. So if I want to calculate f of 0, which condition allows me to put in the 0? The first condition. So I take 0 squared, Seth, and 0 squared is 0. So this is the ordered pair 0, 0. Now I want to calculate f of 1, which condition allows me to plug in 1. The first one, so 1 squared is 1. And what's going to happen here, Abby, is you're going to get a parabola going upwards like this. In that direction.
Like how could you know between the problem we did before we had the straight lines? This one we had the
well, let's say I wanted to calculate this. Which condition?
0.
Which condition allows me to put in a negative 1? So you put the negative 1 here, 0. So this is at the ordered pair negative 1, 0. Now I want to calculate f of negative 2. So which condition allows me to plug in negative 2? Does everyone see that it's this condition here? So I put a negative 2 in this expression. Negative 2 plus 1, negative 1.
Will it be a straight line because it's not squared?
Yeah, it will be a straight line. So it's going to go in this direction, but I need to figure out what happens here. So does this condition allow me to put in 0? It doesn't, so that's why it's going to be an open hole. Because, for example, what about negative 0.01? Is negative 0.01 less than 0? It is. It's less than 0. It's really close to 0, isn't it? So if I put negative 0.01 in this expression, what I'm going to get, Seth, is 0.99, which is really close to what? 1. So what's happening here is I have an open hole at the y value of 1 at the ordered pair 0, 1. So even though I'm not allowed to plug in 0 in this expression, I do it so that I know where my open hole is. My open hole here is right at 0, 1. So this is what my piecewise function looks like. It's a line when x is less than 0, and it's a parabola when x is greater than or equal to 0.
Is there an open hole for the first equation?
An open hole for the first equation. What's
First
the?
one, like x squared.
This is just part of the whole function. See, this is defined as x squared as long as x is greater than or equal to 0. So choose a number for me.
Oh, because it's greater than or equal to?
Greater than or equal to 0. So can I plug 0 in for this?
Right, yeah.
I can. So there's no hole there. This is not an open hole. This is a closed hole because this condition allows me to plug the number 0 in. Because x is greater than or equal to 0.
What if you plugged in something that wasn't greater than? Would you have an open hole there? You can plug in like -1.
Well, we did that. Is negative 1 less than 0?
No, I mean like put negative 1 into the first part.
You can't. The condition doesn't allow it. Negative 1 is not greater than or equal to 0.
But you plug 0 into the second one when you couldn't.
That's exactly... No. Okay. Why did I do that? Why did I plug 0 into the second one when I couldn't? Because the reason why I plugged 0 into this condition was not to fill in an ordered pair, but because I can choose... Let me choose this number again. Let me choose another number that's even smaller. This number. Now, is this number here less than 0? Yes. So I would plug it into here, right? Right? What would I get if I plug this number into here? Into this expression? 0.999. That number is really close to what? 1, right? Does that make sense? The reason why I'm putting an open hole here is because this line is approaching 1, but I can't let it equal 1. I can't fill that hole in. Why? Because the condition doesn't allow it. So that's the only reason I have an open hole here, is because the condition doesn't allow it, but I know that the function's getting closer to 1 as I go in that direction. So if I want the limit as x goes to 0 from the left of the function, what that means is that I'm approaching 0 on the x-axis. The question is, what are the ordered pairs approaching as I approach 0 on the x-axis? The y values are approaching what? Will you travel on that curve? It's approaching 1, right? Do you see that? So what is this limit equal to? The number 1. Why? Because as I approach 0 on the x-axis, the ordered pairs get closer and closer and closer to y equals 1. Traveling in this direction on the curve. Now I take the limit as x goes to 0 from the right, which means I'm going in this direction on the x-axis, which means my ordered pairs are traveling in this direction on the curve. So what are they getting closer to as they travel in this direction? As x goes this way, the y value goes this way, and I'm getting closer to what? 0.
So you don't have,
But you don't have no.
there's no open hole, so.
Right, there's no open hole, but that's, whether it's open or closed isn't the point. It's what am I approaching?
Okay.
Just if I could say it, what if they just gave us x plus 1, not a piecewise, just x plus 1, x is less than 0?
Mm-hmm.
Would you have to do something where you approach maybe 1 from the right, or do you just not? Would you not?
X plus 1, where x is less than 0. And I can, how about I'm going to give you another function after this like that.
Alright.
Is the open hole always on the line that is not like greater than or equal to or less than or equal to? It's just greater than.
No. No. The open hole only comes after you graph the pieces, and you notice here that x can't be 0. So I can at least say yes to the fact that this becomes a suspect where the hole would be, because x can't be 0. Now if x can be a number, x can be 0 here, so there's no chance of being a hole here, because if you can allow that value, then it can't be a hole. There's some real number you can assign to 0 by plugging a 0 in the function. It becomes a suspect point. I can't say that that's universally true, though. Okay? So, here's the left-hand limit. Here's the right-hand limit. Do they agree? No, the limit exists. The limit does not exist.
Okay.
So, we say DNE does not exist. All right, let's do another one. F of x. Let's just say f of x is equal to x squared minus 4. One, two, 1, 2, 1, 2, 3, 4. I want to know what the limit as x goes to -2 is from the left of the function.
Wouldn't there be a hole at 2 too?
Why would there be a hole? This isn't piecewise.
Oh.
It has to be piecewise for there to be whole.
You're most like no, okay. No, it doesn't have to be piecewise to be a whole, but this is a polynomial. Is there anything that you can plug into this polynomial and get an undefined value?
2.
2? 2 squared is 4. 4 minus 4 is... You're just thinking 0. Say what? There's no denominators, so there's no fear of getting an undefined value, right? And there's no square root, so there's no fear of getting a complex number, right? This is polynomial. You can put anything you want into this function. So, okay, now, what are we approaching on the x-axis? We're approaching what? The number -2, and it's got to be from the left now. So here's -2, so I'm going in this direction, Seth, on the x-axis, which means my ordered pairs are traveling on the curve in this direction. Does that make sense? So as I approach this direction from the left, and my ordered pairs are coming down, the question is this: what y value are they approaching? 0. Do you see that? They're approaching 0. That's correct. Now we take the other condition. We say the limit as x goes to -2 from the right. Okay. So I'm traveling now in this direction towards -2. My ordered pairs are going this way. My y values are going this way along the curve. What are they approaching as I go towards from the right? 0 again. So now the question is, do the left and the right-hand limits agree? They do agree. Therefore, I really haven't used this a lot, but these 3 little dots, that's called a shorthand. Katie, it's called a shorthand for the word therefore. The limit exists.
It's like a chart.
No. So what I do, Joshua, is I say the limit as x goes to -2 of the function is what? 0. Yes?
Would you have to do it as x approaches 2?
That would be a different problem, but I can definitely say, because you're looking at the graph and you're saying, well, I know that if I plug in 2, I also get 0, right? That would be a different problem, saying, okay, does the limit as x goes to the number 2 of f of x exist? Does it exist? So we make it a new problem. If I approach 2 from the left, are the y values going towards 0? If I approach 2 from the right, do the y values go to 0? So the left and the right hand agree. Therefore, the limit exists, and I can say that the limit is also 0. So you can have, that's a really good question, you can have the limit be the same number for 2 different places, actually more than 2, okay? But we only want to answer the question that's being asked. So the question that was being asked from the beginning of this particular problem was, what is the limit as x goes to -2 from both the left and the right-hand side? Does that make sense?
Yeah.
But you're absolutely right. The limit as x goes to 2 of f of x is also equal to 0. Okay, let's consider.
What if they give you like a limit? Like I'm just looking at the homework. For like 29, it says like the limit of x squared minus 3. How do you find the limit from that?
Was that the function?
No, it said limit of x goes to -4, x squared minus 3. And then parentheses, x squared minus 6. And then it says find the limit.
Find the limit?
How would you do that?
All right, let's graph it. What does x squared minus 3 look like? Let's see here. So 1, 2, 3, 4, which means this thing goes up. I'm going to run out of space here. Yeah. 1, 2, 3, 4. Plug in 4. 4 squared is 16. 16 minus 3 is 13. Is that right?
They give you a graph, but they just ask you to find the limit.
Yep. All right. So there it is. So here's negative 4. So if I approach negative 4 from the left, the ordered pairs are going to go in this direction, Sydney. So what are they approaching? 13. As I approach negative 4 from the right, the ordered pairs are now going this way. What are they approaching? 13.
Okay.
So they approach 13 from both the left and the right. That's the same number, isn't it?
So the limit exists.
The limit exists. Yes. Right, right. Kate basically said you just plug in 4, right, into the expression, and you get 13. That's right. That's called evaluating the limit by direct substitution. Okay? Direct substitution. And you can do that for a lot of functions. You can't do that for all functions because you may get what's called an indeterminate. For example, look at number 25. Look at number 25. 25 says, what is the limit as x goes to 1 of the natural logarithm of 2x minus 1 over x minus 1? Let's use direct substitution on this. So this becomes the natural logarithm of 2 times 1 minus 1 over 1 minus 1. Well, wait a minute. 2 times 1 is what? 2. 2 minus 1? Natural log of 1? 0 over 1 minus 1? That's your special undefined number called a what? An indeterminate, but that doesn't mean the limit doesn't exist. So now you have to approach it from the left and the right to see if it's approaching the same thing. You have to graph it, or you're going to have to use the calculator, the tables. Okay? That gets us started off. All right. God bless you wherever you are today.